welcome to this problem walkthrough. Today, we will explore an interesting problem titled Shuffle the Array, where we'll learn how to rearrange an array based on given constraints. Let's dive in and understand the problem step by step. Sit back, and let's get started. In this problem, you are given an array called nums that contains two n elements. These elements are organized such that the first n elements represent one group, x1, x2, xn, and the next n elements represent another group, y1, y2, yn. The task is to rearrange the array so that elements from these two groups are interleaved. Specifically, the array should be returned in the format x1, y1, x2, y2, xn, yn. Let's also look at the input and output format. The input consists of the nums array, where its length is 2n and ranges between 2 and 20,000 elements. Additionally, you are given an integer n, which is half the length of the array and is guaranteed to be between 1 and 500. The output is the shuffled array, where elements from the two groups are interleaved as specified. For clarity, let's consider an example. Suppose the input array is nums equals 2, 5, 1, 3, 4, 7, and n equals 3. The array is divided into two parts. The first n elements, 2, 5, 1, represent the group x1, x2, x3, and the remaining n elements, 3, 4, 7, represent the group y1, y2, y3. The goal is to construct a new array by alternating between these two groups, starting with the first element of the x group, then the first element of the y group, and so on. The resulting shuffled array is 2, 3, 5, 4, 1, 7. Another example highlights how this works with a larger value of n. If nums equals 1, 2, 3, 4, 4, 3, 2, 1, and n equals 4, the array is split into 1, 2, 3, 4, and 4, 3, 2, 1. Interleaving these groups results in 1, 4, 2, 3, 3, 2, 4, 1. Let's break down another example to solidify the concept. Consider nums equals 1, 1, 2, 2, with n equals 2. The array is divided into two parts, 1, 1 for the x group and 2, 2 for the y group. To create the shuffled array, we alternate between elements from these two groups. Starting with the first element of the x group, followed by the first element of the y group, and so on, we construct 1, 2, 1, 2. This highlights how the structure of the solution relies on indexing and grouping, ensuring that the interleaving is consistent. To further ensure clarity, let's discuss the constraints and edge cases. The value of n ranges from 1 to 500, and the array length is always 2n. Each element in nums is an integer between 1 and 1000. For edge cases, when n equals 1, the array has only two elements, such as nums equals x1, y1, and the output is simply x1, y1. For the maximum input size, when n equals 500, the array contains 1000 elements, so the solution must manage large inputs efficiently. Another edge case occurs when all elements in the array are identical, like nums equals 1, 1, 1, 1, where the output remains 1, 1, 1, 1. Lastly, the input array's order does not matter. The solution depends only on the index-based grouping of elements, ensuring the shuffle is always performed correctly. To begin with, we can think about the brute force approach, which relies on manually constructing the shuffled array. The idea here is straightforward. The given array is split into two halves, where the first half holds elements like x1, x2, and so on, and the second half holds elements like y1, y2, and so forth. To create the shuffled array, we alternate between picking elements from each half. For instance, we take x1 from the first half, then y1 from the second half, and continue this alternation. Implementation-wise, we create an empty result array and traverse both halves in parallel, inserting one element from each part alternately. This approach has a time complexity of O(n), since we iterate through the array once, and a space complexity of O(n), due to the additional array we use for storing the result. While this method is simple and works well for smaller inputs, it has a trade-off. It uses extra memory for the result array, which isn't ideal if we want to optimize for space. Now, let's consider an optimized approach that focuses on performing the transformation in place. The intuition behind this is to avoid the overhead of creating a new array by rearranging the elements directly within the given array. This would minimize memory usage, keeping the space complexity at O(1). However, the challenge with this approach lies in managing the overlap between the two halves of the array. Since the elements of both halves are interleaved during the shuffle, there's a risk of overwriting data or requiring complex transformations to keep track of the original values. As a result, while this approach theoretically minimizes memory usage, it is not practical for this problem. The potential for data loss and the additional complexity make it less appealing, especially when simpler and more efficient alternatives are available. Next, we arrive at a more practical and efficient solution, the direct index mapping approach. Here, we take advantage of the array's structure, where the first half contains elements x1 through xn, and the second half contains elements y1 through yn. By recognizing this structure, we can directly map indices during traversal. For each index I in the range from 0 to n1, the element from the first half corresponds to nums, I, and the element from the second half corresponds to nums, n plus I. Using this mapping, we construct the shuffled array by iterating through the original array once and alternately adding nums, I, and nums, n plus I, to a result array. This approach has a time complexity of O, n, as we traverse the array once, and a space complexity of O, n, due to the additional result array. The trade-offs here are minimal. The method is simple, efficient, and avoids the challenges associated with in-place transformations. Overall, this makes it the most practical choice for solving the problem. Ultimately, we chose the direct index mapping approach as our strategy because it strikes the right balance between simplicity, efficiency, and clarity. While the brute force approach is a valid option, it doesn't offer any advantage over direct mapping in terms of time or space complexity. On the other hand, in-place transformation, though theoretically space-efficient, is overly complex and poses significant risks of data corruption. The key insights that led us to the direct mapping method include the predictable structure of the array, which allows elements to be mapped cleanly using indices, and the realization that constructing a new array ensures an efficient and straightforward implementation. The final trade-off to consider is the O, n, space complexity due to the result array, but given that the time complexity is also optimal at O, n, this approach represents the most balanced and practical solution for the problem. In this problem, we are given an array of size 2n, where the first half contains elements labeled as x1, x2, xn, and the second half contains elements labeled as y1, y2, yn. The goal is to create a new array in which we alternate between elements from the first and second halves. For example, our output should look like x1, y1, x2, y2, xn, yn. To achieve this, we start by understanding the input and output. The input is a list ARR of size 2n, and the output is another list of the same size, but with elements arranged in the desired order. To implement this, we first initialize an empty list called result to store the shuffled elements. This list will dynamically grow as we append elements one by one. Then, we loop through the indices of the first half of the array, which range from I equals 0 to I equals n1. During each iteration of this loop, we will alternate between elements from the two halves of the array to build the result step by step. For each iteration in the loop, the algorithm performs two main operations. First, it appends the ith element from the first half of the array, ARR, I, to the result list. Then, it appends the ith element from the second half, which is located at ARR, n plus I, to the same result list. These two steps ensure that we are alternating consistently between the two halves of the input array. After the loop completes, the result list contains all the elements in the desired order, and we simply return it as the output. To break this process down further, there are a few key insights that make the algorithm efficient. First, the array is conceptually divided into two groups of equal size, and by alternating between the two groups, we can construct the output in just one pass through the array. This gives the algorithm a time complexity of O, n, where n is half the size of the input array. Additionally, it handles edge cases well, such as when the input contains only two elements, since the loop still alternates between them correctly. The algorithm is also designed to handle large inputs efficiently thanks to its linear time complexity. Regardless of how large the input array is, the loop will only iterate through n indices, making it scalable. In terms of space complexity, the only additional space we use is for the result list, which grows dynamically as we append elements in the shuffled order. This results in a space complexity of O, n, proportional to the size of the input. Now, let's look at the data structures used. The input array ARR is a key component, as it allows us to access elements from both halves in constant time. This random access capability is crucial for the algorithm's efficiency. The result list is another important data structure, as it is where we build the shuffled output step by step. Its dynamic nature ensures that we can append elements as we go, maintaining the required order without any additional processing. Together, these data structures enable us to achieve the desired output with minimal overhead. To understand how the algorithm works in practice, let's look at its implementation in Python. The function shuffle_array starts by calculating n, which is half the size of the input array. This determines the boundaries of the two halves. Next, it initializes the result list as empty. The main logic is implemented in a loop that iterates from 0 to n1. Inside the loop, we append two elements to result in each iteration. First, we take the element from the ith position of the first half, which is arr, I. Then, we take the element from the ith position of the second half, located at arr, n plus I. These two operations ensure that the elements from both halves are interleaved in the correct order. Finally, after the loop completes, the result list contains all elements arranged in the shuffled order, and the function returns this list as the output. To see the algorithm in action, let's walk through an example. Suppose the input array is arr equals 2, 5, 1, 3, 4, 7. Here, the first half is 2, 5, 1, and the second half is 3, 4, 7. We start by initializing an empty result list. In the first iteration, where I equals 0, we append the first element of the first half, which is 2, to result. Then, we append the first element of the second half, which is 3. At the end of this step, result becomes 2, 3. In the second iteration, where I equals 1, we append the second element of the first half, 5, followed by the second element of the second half, 4. Now, result is 2, 3, 5, 4. In the third and final iteration, where I equals 2, we append the third element of the first half, 1, and the third element of the second half, 7. The final result list is 2, 3, 5, 4, 1, 7, which we return as the output. When analyzing the algorithm's complexity, we find that its time complexity is O(n). This is because the loop iterates n times, and each append operation inside the loop takes constant time, O(1). As a result, the total time required is proportional to the size of the input, which is highly efficient. In terms of space complexity, the algorithm uses O(n) additional space for the result list. The space required grows linearly with the size of the input, making it suitable for handling larger arrays. Overall, this algorithm is both time-efficient and space-efficient, making it a robust solution for the problem of shuffling the array in alternating order. This code solves the LeetCode problem number 1470, Shuffle the Array, where we are tasked with rearranging an input array of length 2n such that elements alternate between the first half and second half of the array. The solution is implemented in the shuffle method of the solution class. First, an empty list result is initialized to store the shuffled elements. We then iterate through the range of n, which corresponds to the length of the first half of the array. For each index I in this range, two elements are added to the result list in sequence. The first is nums, I, representing the ith element from the first half of the array. The second is nums, I plus n, representing the corresponding ith element from the second half of the array, offset by n. This ensures that we alternate between elements from the first and second halves of the array, achieving the desired shuffle. Once all elements have been added, the result list is returned as the output. This approach is efficient, with a time complexity of O(n), since we iterate through the array once, and a space complexity of O(n), due to the additional list used to store the result. The solution handles all valid inputs, including edge cases such as the minimum input size where n equals 1. This Java implementation solves LeetCode problem number 1470 Shuffle the Array by mirroring the logic provided in the Python solution. It uses a single loop to alternate elements from the first and second halves of the input array into a new result array. Key differences include Java's use of typed arrays, int, explicit initialization of the result array, and standard Java syntax for array manipulation. The solution is efficient, operating in O(n) time complexity, where n is the length of one half of the input array. Here, we begin with a basic input case to understand how the solution works step by step. The input array is nums equals 2, 5, 1, 3, 4, 7, and n equals 3. First, we initialize an empty list called result to store the shuffled output. Then, we split the nums array into two parts. The first half consists of the first n elements, which are 2, 5, 1. The second half consists of the remaining elements, from index n to the end, which are 3, 4, 7. Now, we start the iteration process. In the first iteration, when I equals 0, we add the first element from the first half, nums 0, which is 2, to the result. Then, we add the first element from the second half, nums 3, which is 3. Our result becomes 2, 3. In the second iteration, when I equals 1, we add the second element from the first half, nums 1, which is 5, followed by the second element from the second half, nums 4, which is 4. Now, the result becomes 2, 3, 5, 4. Continuing with the example, in the third iteration, when I equals 2, we take the third element from the first half, nums 2, which is 1, and add it to the result. Then, we take the third element from the second half, nums 5, which is 7, and add it as well. At this point, the result becomes 2, 3, 5, 4, 1, 7. With all iterations complete, we arrive at the final output, which is 2, 3, 5, 4, 1, 7. Now, let's examine a larger input to reinforce the process. The input array is nums equals 1, 2, 3, 4, 4, 3, 2, 1, and n equals 4. Again, we start by initializing an empty result list. The nums array is divided into two parts. The first half is 1, 2, 3, 4, and the second half is 4, 3, 2, 1. This sets up the two halves for the shuffle process. Now, we begin iterating over the elements, one index at a time. For the first iteration, when I equals 0, we add the first element from the first half, nums 0, which is 1, followed by the first element from the second half, nums 4, which is 4. This makes the result 1, 4. In the second iteration, when I equals 1, we add the second element from the first half, nums 1, which is 2, and then the second element from the second half, nums 5, which is 3. The result now becomes 1, 4, 2, 3. In the third iteration, when I equals 2, we continue the pattern by adding nums 2 from the first half, which is 3, and nums 6 from the second half, which is 2. The result grows to 1, 4, 2, 3, 3, 2. Finally, in the fourth iteration, when I equals 3, we add nums 3 from the first half, which is 4, and nums 7 from the second half, which is 1. This completes the shuffle, and the result is 1, 4, 2, 3, 3, 2, 4, 1. The final output is exactly what we expected. In the last example, we look at an edge case with the input nums equals 1, 1, 2, 2, and n equals 2. As always, we start by initializing the result as an empty list. Then, we split the nums array into two parts. The first half contains 1, 1, while the second half contains 2, 2. During the first iteration, when I equals 0, we add the first element from the first half, nums 0, which is 1, followed by the first element from the second half, nums 2, which is 2. This gives us a result of 1, 2. In the second iteration, when I equals 1, we add the second element from the first half, nums 1, which is 1, followed by the second element from the second half, nums 3, which is 2. The final result becomes 1, 2, 1, 2. Since all iterations are complete, the output for this edge case is 1, 2, 1, 2. This confirms that the solution handles edge cases correctly and maintains a consistent pattern. In terms of time complexity, the algorithm processes the input array nums in a structured manner to produce the shuffled output. First, initializing an empty list result is a constant time operation, O1, as it simply creates an empty container. Next, the core of the work happens inside the for loop, which iterates n times, where n is half the size of the input array. During each iteration, there are two append operations, adding the element from the first half of the array and then adding the corresponding element from the second half. Each of these append operations is O1, assuming amortized complexity for list appends in Python. Thus, each iteration involves O(1) work, and over n iterations, this totals to O(n). Finally, the return statement, which simply hands back the result list, is also O(1), as it doesn't involve copying or manipulating the list. When we combine all these steps, the overall time complexity of the algorithm is O(n). Now, let's examine the space complexity. The input array nums has a size of 2n, but we don't count this as additional space since it's part of the input itself. The additional memory usage comes from the result list, which is used to store the shuffled output. Over the course of the algorithm, result grows to hold 2n elements, matching the size of the input. This contributes O(2n) additional space, which simplifies to O(n) in big O notation. Aside from this, there are no other significant memory allocations or data structures used. The loop variable I is a simple integer and uses constant space, O(1). Therefore, the overall space complexity is O(n), driven entirely by the size of the result list. Let's compare this approach to a brute force alternative. A naive implementation might involve iterating through the input array twice, once to collect elements from the first half and again for the second half, followed by concatenating the two lists. While this would still result in O(n) time complexity overall, the implementation would be less efficient due to the extra intermediate steps and would likely be harder to understand. In contrast, the provided optimal algorithm processes each element exactly once and appends directly to the result list, making it both concise and efficient. Furthermore, the algorithm's time and space complexities remain consistent across all cases: best, average, and worst. Regardless of the input configuration, the loop processes every element in constant time, leading to O(n) time complexity. Similarly, the size of the result list is always proportional to the input, giving an O(n) space complexity. To solidify our understanding, let's break down the big O proof for this algorithm. The time complexity is determined by the number of iterations in the loop, which is directly proportional to n. Since each iteration involves constant time operations, the total time taken is O(n). For space complexity, the result list grows proportionally with the input size. Specifically, for an input of size 2n, the output list also contains 2n elements, resulting in additional space usage of O(n). There are no other significant memory requirements. In conclusion, the algorithm achieves O(n) time and O(n) space complexities, demonstrating that it is both efficient and well-suited for solving the problem. When tackling shuffle problems, there are several common mistakes to watch out for. First, not handling input constraints properly can lead to issues, especially if you assume the input array always has an even length. While some problems guarantee valid input, in interviews, you should clarify constraints and handle edge cases, like an odd-length array, to demonstrate thoroughness. Next, modifying the original input array can be problematic. Many problems expect you to return results without changing the input, so altering it accidentally can lead to incorrect outputs and failing test cases. Another frequent oversight is using extra space when the problem explicitly requires an in-place solution. This increases your space complexity unnecessarily and may cost you points in an interview. Finally, be cautious with indexing during alternation. When alternating between two subarrays, mixing up indices or incrementing the wrong variable can lead to out-of-bounds errors or incorrect outputs. Carefully managing your indices is key to avoiding these bugs. Over-engineering solutions is another common pitfall. For problems that are inherently straightforward, introducing overly complex data structures or algorithms can make your code inefficient and harder to debug. Always aim for the simplest correct solution first. Now, let's touch on some interview insights. Fully understanding the problem is critical. In shuffle or rearrangement tasks, clarifying constraints like array length or input validity with your interviewer can help you avoid misunderstandings. Testing edge cases is also crucial. Consider scenarios like empty arrays, single-element arrays, or arrays with repetitive values. Time complexity awareness is another important aspect. If an O(n) solution is achievable, you should avoid settling for less optimal approaches like O(n squared). Finally, communicate your thought process clearly, especially when working with indices. Index handling is a common source of mistakes, so walking your interviewer through your logic can help you catch errors early and demonstrate your reasoning skills. Shuffle problems are closely related to several other common array manipulation tasks. For example, LeetCode 1920 challenges you to build an array from a permutation, while LeetCode 384 involves shuffling an array randomly. Another related problem is LeetCode 905, which asks you to sort an array by parity. Exploring these problems can deepen your understanding of array rearrangement techniques. Now, let's look at some alternative approaches to solving shuffle problems. The two-pointer technique is one option. Here, you use two pointers to traverse the two subarrays and directly insert elements into the result. This method is intuitive and simplifies the logic but does require an extra space to store the result. Another approach is in-place rearrangement. Instead of using extra space, you manipulate the original array directly through index transformations or cyclic swaps. While this saves space, it can be harder to debug due to the complexity of managing the indices correctly. Both approaches have their trade-offs, so choose based on the problem's requirements. Finally, let's discuss the recursive approach. This method involves dividing the array recursively into smaller chunks, shuffling those chunks individually, and then combining the results. While this approach can help with conceptual understanding of divide and conquer techniques, it adds the overhead of recursion and is rarely the most optimal solution in practice. Its main value lies in broadening your perspective on how to approach shuffle problems, so it's worth exploring for educational purposes, but it's not typically the best choice for implementation in competitive coding or interviews. Great job following along. To summarize, we reviewed how to shuffle an array efficiently with a focus on optimal time and space usage. Remember to practice similar problems to strengthen your problem-solving skills. Thanks for watching, and see you in the next walkthrough. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!